Writing in the comment section whether audio and video everything is perfect or not. Great. So now we are on the finite state machine, but before going towards the finite state machine, one very important topic: designing of desired synchronous counter, ring counter and twisted ring counter, which is a part of the last lecture. We'll discuss first and then we will move towards the Mealy and Murray model. Hoping all of you are ready. Great. So please let me know by writing in the comment section, beta ji, whether audio and video everything is going perfect. So your today's topic that we are going to discuss is designing of the different types of synchronous counters. Then we will see ring counter and a twisted ring counter. Later on we will move towards finite state machine, that is FSM part 1. I have made two parts for the FSM. So first we will discuss about the finite state machine part 1, in which we are going to discuss the Mealy and Murray model. All of you are ready? Please let me know by writing in the comment section, beta ji. I need your response. I need your response. I need your response, beta ji. Great. So in the last lecture, already I have discussed about designing of synchronous counter. Steps to design synchronous counter. Steps to design synchronous counter. So let's discuss about the steps to design synchronous counters first. Great. Now please observe, step number 1, whenever we want to design any desired synchronous counter, first of all we have to identify the number of different states required. That will give the information of number of flip-flops needed. Okay. Now please observe here. Step 1 is to find number of flip-flops required by using relation m is less than or equals to 2 to the power n. Suppose if I am interested to design a mod 4 counter, then n will be equals to 2 because m is 4. Mod 4 means 4 different states are required. So m is 4 and n you can calculate, m is less than or equals to 2 to the power n. So n will become 2. If you want to design mod 5 counter, then we need n is equals to 3. Is it okay? Yes, sir. Next is to choose the type of flip-flop which you want to use. Is it okay? We always select such a flip-flop which will reduces the delay. For designing any desired circuit, we always choose such a flip-flop which reduces the delay. Is it okay? Next is step 3, construct a state table of required counter. Whatever counter you want to design, for that you have to first construct a state table. Now from the state table you can construct excitation table and use K-map to minimize excitation equation. Is it okay? Next is implement the logic circuit. Only you have to follow these 5 steps to design any desired synchronous counter. Any desired synchronous counter. Is it okay? How many of you able to understand? How many of you able to understand these 5 points, beta ji? Please let me know by writing in the comment section. Please let me know by writing in the comment section. Great. So let's design one desired flip-flop. Okay. Let us first discuss. I am interested to design, or let me make it simple. First question, I just wanted to make it as easy as possible, and also you are going to decide what counter you want to design. Okay. So please observe these steps through one question. Okay. Design synchronous counter. Design synchronous counter for the count sequence design synchronous counter for the count sequence. Whatever count sequence you want, you can tell me. Any count sequence from 0 to 4 or 0 to 7. You can take any count sequence from 0 to 7 or 0 to 4. Let's take a count sequence. Let us suppose initial state is a 0, and on applying the clock, you want next state to be the binary of 3, and on applying next clock, you want next state to be a binary of 1. On applying next clock pulse, you want the next state to be a binary of 2, and then on applying fourth clock, again you want the binary appeared onto the counter as a 0. So suppose we want to design a counter for the count sequence 0, 3, 1, 2. Is it okay? 0, 3, 1, 2, 0. You want to design such a counter. Any flip-flop you can use by using D flip-flop. Okay. Presently, I want to create it by using D flip-flop. How many of you able to understand the question? So we want to design a circuit, a synchronous counter, which counts the sequence 0, 3, 1, 2, 0. How to design? Step 1 suggests. Now please observe the steps. Step 1 suggests find the number of flip-flops required. So as per step number 1, please observe beta ji. Step 1, m is less than or equals to 2 to the power n. So how many number of different states we have? 0, the highest number in the sequence is 3, and the minimum number of bits with which we can represent 3 is 2 bit. You can represent 1, 1. 3 can be represent minimum 2 bit. Is it okay? So the highest number is 3 and we can represent minimum by 2 bit. It means we can have how many number of states? 0, 0, 1, 1, 1, 0 and 0, 1 and 1, 0. Is it okay? So how many number of state? We have 4 states. 4 different state needed, 2 to the power n. So that indicate n is equals to 2. That is 2 D flip-flops are required. 2 D flip-flops required for desired counter. For desired counter. How many of you able to understand up to this part, beta ji? Step 2. Now what is the step 2? Step 2 says choose the type of flip-flop. Already we have chosen a D flip-flop. Is it okay? So in step 2 we have to choose the type of flip-flop. So since in the question already D flip-flop is given, so you have to choose D flip-flop now. Next is construct a state table of the required counter. Next is construct a state table of the required counter. So first of all you have to, step number 3, please observe beta ji, please observe. Step 3, state table. Now how to construct a state table? Please observe. In a state table we have present state, then we have next state, logic. Okay, and step number 4 says excitation table. So we have to construct the excitation table of the flip-flop with which we want to design based upon the present state and next desired state. So here I am writing excitation on D flip-flop. Excitation on D flip-flop. Is it okay, beta ji? Yes, sir. Now please observe. We have present state, next state, and excitation needed onto the D flip-flop. Is it okay? Yes, sir. Present state, we have 2 bits. If we choose 2 flip-flop, then we have 2 bits, 2 flip-flop. Each flip-flop can store only 1 bit. So 2 bit for 2 bit, I am just using the notation as Q1 and Q0. Okay. and the next state will become Q1 plus 1 and Q0 plus 1. Excitation needed onto the D0 or onto the D1, onto the D1 and onto the D0. Is it okay? Yes, sir. Now please observe. We want, sir, the present state. The present state we want 0, 0. So if the present state is 0, 0, then on application of the clock, you want next state binary of 3. Binary of 3 will be indicated as 1, 1. If the present state is 0, 0, you want next state to be 1, 1. If the present state is 1, 1, you want next state to be 0, 1, binary of 1. Is it okay? Yes, sir. If the present state is a 0, 1, if the present state is a 0, 1, you want next state to be 1, 0. If the present state is 1, 0, you want next state to be 0, 0. So accordingly, you can fill the present state and next desired state table. Please let me know by writing in the comment section. Are you able to understand up to this part, beta ji? Great. So now we know about the present state and next state. Next is to write the excitation table. So excitation table of the required flip-flop based upon the present state and next state required. We all know about the excitation table of D flip-flop. In D flip-flop, based upon Qn and Qn plus 1, we can have excitation onto D. We all know D flip-flop is a transparent latch. It means whatever value of Qn plus 1 needed, same need to be applied onto the D flip-flop. Is it okay? So in the rough, I am just using this excitation table of D flip-flop. All of you are aware with the excitation table of D flip-flop. It is excitation table of D flip-flop suggests you can need to apply the excitation on D same as required on Qn plus 1. So now please observe. I first identify Q1 and Q1 plus 1. It means the flip-flop 1 present state and required next state. For present state 0, next required state 1. For present state 0, next required state 1. What is the excitation needed onto the flip-flop 1? Sir, we need excitation 1. How many of you able to understand? In the same way, for present state 1, next required state 0. Present state 1, next required state 0. Excitation required onto the D flip-flop is 0. Present state 0, next required state 1. Present state 0, next required state 1. Q1, 0 and Q1 plus 1 is the next state onto the flip-flop. Excitation needed onto the flip-flop is 1. Present state 1, next required state 0. For present state 1, next required state 0, excitation needed onto the flip-flop is 0. So you can just copy paste Q1 plus 1 onto the D because D flip-flop is a transparent latch. Is it okay? How many of you able to understand? In the same way, observe Q0 and Q0 plus 1. So if you observe Q0 and Q0 plus 1, present state onto the flip-flop, not present state onto the flip-flop D0, and next state required from the flip-flop D0 is 0, 1. So for 0, 1, excitation needed onto D0 is equals to 1. In the same way, if you observe for 1, 1, we need to apply 1. For 1, 0, present state 1, next required state 0, we need to apply excitation as 0. And for 0, 0, we need to apply excitation 0. How many of you able to understand up to this part, beta ji? It can be any flip-flop. For any flip-flop, you have to follow the same procedure. Is it okay? Yes, sir. Next is to write the excitation equation. We have to observe D1 and D0. What are the inputs that we can apply onto the flip-flop? Only present input or present state. So present state is Q1 and Q0. In terms of Q1 and Q0, this 0, 0 is indicating binary of 0. This 0, 1 is indicating binary of 3. 1, 0 is indicating binary of 1. 1, 0 is 0, 1 is indicating binary of 1. And 1, 0 is indicating binary of 2. Is it okay? Yes, sir. Now please observe where we are getting output logic high for D1 in terms of Q1 MSB, Q0, LSB. Sir, we are getting high, binary high onto the binary condition of 0. We are getting logic high onto the binary condition of 0, and we are getting binary D1 high onto the binary condition of 1. So 0, 1. How many of you able to understand? Now we can do the minimization by using K-map. Okay. Now please observe here. Q1 is a MSB, so Q1 complement Q1, Q0 complement Q0, 0, 1, 2, 3. We are getting logic 1. So there is a pair, and with this pair we have the minimized expression onto the D1 required in order to get the desired is Q1 complement. How many of you able to understand up to this part? Please let me know by writing the comment section, beta ji. So onto the binary of 0 and onto the binary of 1, we are getting high onto the binary of 0 and onto the binary of 1. If Q1 is MSB and Q0 is a LSB, we can only apply a present input or a present state. Is it okay? Onto the flip-flop. So now we know about D1. D1 is equals to Q1 complement. Similarly, observe for D0. So D0 we are getting high onto the binary of 0 and 3. Onto the binary of 0 and 3. D0 we are getting high onto the binary condition of 0 and 3. So we can do the minimization. We have Q1 complement Q1, Q0 complement Q0, 0, 1, 2, 3. We are getting high on these two conditions. So D0 will become Q1 complement Q0 complement plus of Q1 Q0. Is it okay? Yes, sir. It indicates we have D0 equals to Q1 XNOR Q0. Is it okay, beta ji? Please observe. So they may ask you in the synchronous counter, they may give you this count sequence and ask you find the input required onto the D flip-flop for the required count sequence counter. So, and in the options they will give you these equations that D1 is equals to Q1 complement or D0 is equals to Q1 XNOR Q0. Maybe they will give the circuit. Step number 4 is your circuit implementation. Step 5 is your circuit implementation. If we talk about circuit implementation, we have two D flip-flop. We have two D flip-flop, one and another one. Okay? Yes, sir. So I am using this D1, Q1 complement, D0, Q0 complement. Since this is a synchronous counter, in a synchronous counter, all flip-flops are connected with the same clock pulse. Either you can use negative S triggered or positive S triggered. It is up to you. But all are going to initiate their operation at the same clock. All are connected with the same clock. D1 is connected with Q1 complement. So I am using this. D1 is connected with Q1 complement. D1 is connected with Q1 complement. And D0 is Q1 XNOR Q0. Q1 XNOR Q0. The circuit is implemented. In order for the circuit to operate satisfactorily, we must need to keep the time period of the clock such that all the logic gates will operated before the clock came. So before the next clock came, as well as the flip-flop will operate. Since both the flip-flops are connected to the same clock, so only one TPDFF, propagation delay of the flip-flop, and one propagation delay of XOR gate. If your time period of the clock is greater than, if the time period of the clock is greater than or equals to, TPDFF, where TPDFF is the propagation delay of flip-flop. Both are identical flip-flop, okay, and TPD of XOR gate. So if you give that much of time period of the clock, then satisfactory operation of your this particular circuit happen. How many of you now able to understand up to this part? Great. They may also give you great beta ji. If you have completed, it is very good. You can do the revision. If you have already completed, you can do the revision. If your revision is also done, then you can proceed for the next subject. Is it okay? Great. Now, please observe here. So, up to this part, I am hoping everything is clear. One type of question they will give you in the question they may give you the count sequence and ask to find out the logical expression onto the flip-flops for the desired counter. They may give you this circuit, or they may give you only this circuit and ask to identify the count sequence obtained from the counter, synchronous counter shown below. So how to identify the count sequence? Please observe here. How to identify the count sequence? For that, first of all, we will use clock and Q1 and Q0. Already I told you to solve any question based on the sequential circuits. To solve any question based on the sequential circuits, we have to follow a thumb rule. What is the thumb rule? Thumb rule says to any question of the sequential circuit, thumb rule says before applying clock pulse, first find input to the flip-flop, then apply clock pulse and follow the truth table. That is all you have to use to solve. Almost 90% of the questions are going to solve with this one line technique. Before applying clock pulse, first find input to the flip-flop, then apply clock pulse and follow the truth table. Okay. Now please observe here. In case if the initial state is not given, you can consider before applying clock initial state as 0, 0 of any circuit. Is it okay? If the initial state is given, you have to write down before applying the clock, it means on the 0th clock pulse, you have to write that particular state. If it is not given, you can consider it 0, 0. Now, on application of first clock, what happened? Before applying first clock, first find input to the flip-flop. Now see, Q1 is 0. When Q1 is 0, Q1 bar is logic level 1. So it means D1 is 1. Is it okay? Yes, sir. Before applying first clock pulse, and if you observe here, Q1 is a 0 as well as Q0 is a 0. XNOR gate is an equivalence detector. So when both are 0, 0, this will become 1. So before applying first clock pulse, first find input to the flip-flop. Now apply clock pulse and follow the truth table. We all know about D flip-flop. In a D flip-flop, whatever input we will give, same we get at the output. That is why it is called as delayed flip-flop. So onto D1 we have 1. So on application of clock we get 1. On D0 we have 1. So on application of clock in the latch of D flip-flop, 1 get stored. Is it okay? So the state after first clock pulse will become 1, 1. Now please observe before applying second clock pulse. Before applying second clock pulse, again first find input to the flip-flop. Before applying second clock pulse, first find input to the flip-flop. What is the present status? Present status is this is 1 and this is 1. Q1 is 1 and Q0 is 1. Is it okay? Now before applying second clock pulse, first find input to the flip-flop. If Q1 is 1, then its complement is 0. Yes, sir. And if both are 1, 1, here we are getting 1 because XNOR gate is a equivalence detector. So both the input of XNOR gate is 1. So its output will become 1. Now 1 is the input to D1 and 1 is the 0 is the input to D1 and 1 is the input to D0. On application of the clock, we get 0, 1 get stored here. Is it okay? Yes, sir. Now before applying second clock pulse, first find input to the flip-flop. What is the present state? Before applying third clock pulse, first find input to the flip-flop. What is the present status after second clock pulse? 0, 1 is stored onto the latches of D flip-flop. Now, if 0, then its complement is 1. So here we are getting 1. This is 1, 1, 0 different. So here we are getting 0. So onto the flip-flop D1 we are getting 1 and onto the flip-flop D0 we are getting 0. On application of the clock we get 1, 0. Great, sir. What happens on fourth clock pulse? Now this is the present state. What happens onto the fourth clock pulse? Before applying fourth clock pulse, first find input to the flip-flop. Before applying fourth clock pulse, first find input to the flip-flop. So what is the input to the flip-flop? After third clock pulse, this is the input to the flip-flop. This is the flip-flop status. Now, if this is 1, its complement is 0, and if this is 0, we are getting here 0. So 0, 1, we are getting 0. Onto the D0 we have 0, onto the D1 we have 0. On application of the clock, both the flip-flops stores 1, 1. Sorry, both the flip-flops stores 0, 0, because we are giving 0, 0. So what is the sequence we are getting? If a binary of 0 available, then on application of the clock we are getting binary of 3. If binary of 3 available, then on application of clock we are getting binary of 1. If binary of 1, then on application of the clock we are getting binary of 2. If binary of 2, then on an application of the clock we are getting binary of 0. We want to design 0, 3, 1, 2, and we are getting 0, 3, 1, 2. How many of you able to understand how to design any desired synchronous counter? Can you please tell me by writing in the comment section, beta ji? Great, beta, great. If you increase the number by doing number of questions, na, if you increase as much as possible, na, go with the first with the PYQ of GATE, then PYQ of engineering services, conventional of engineering services, only your numerical type part or a theoretical question you can skip. Only follow the conceptual or numerical type questions of conventional, and if you complete that, then move towards Indian administrative services. Okay, PYQs. So that will help you a lot and covers almost entire part of your syllabus. Is it okay? If you further have a time, you can go with a number of different test series questions and your different question banks. Okay, great. How many of you able to understand up to this part? If I ask you to design a synchronous series carry counter, can you design a synchronous series carry up counter? Yes, sir. The same process we will follow. Process is, step 1 is, first find out the number of flip-flops required with the relation m less than or equals to 2 to the power n. In most of the PSUs, only this part is asked. They ask how many number of flip-flops are required to design a count in 7321, and you can easily observe. Next is choose the type of flip-flop. Most of the time in objective questions, type of flip-flop is already mentioned to you. Construct a state table of the required counter, and then construct excitation table of the flip-flop with which you want to design your required counter. Okay, minimize the excitation equation and implement the logic circuit. So now you can design any desired synchronous counter. Is it okay? Let us suppose we have already one designed synchronous counter and we have to analyze the different states. Okay, so how to analyze the different state, and also we'll discuss about the synchronous series carry up counter. We have seen in the last class ripple counter and a ripple up counter we have seen. Now let's observe synchronous series carry up counter. Please observe here. If you want, you can design by using T flip-flop, very simple, simply as we did for the last question. Suppose we have already a designed circuit of synchronous carry up counter. I'm using 4-bit. Okay, by using T flip-flop, T Q Q bar, T Q Q bar, T Q Q bar, T Q Q bar. Always remember, synchronous counter is one in which all the flip-flops are connected with the same clock pulse. Is it okay? Yes, sir. Now T is equals to 1, and this will be your least significant bit, next significant bit. Okay, next significant bit, and next significant bit. The same process goes on for n number of bits synchronous series carry up counter. Presently I am representing a 4-bit synchronous series carry up counter. Is it okay? Now how to analyze such a circuit? You can easily observe Q naught, since T naught is equals to 1, so Q naught toggles on every positive edge triggered clock. Yes sir. So first observation is Q naught toggles on each clock. Yes sir. If you observe Q1 toggles. See, we all have T flip-flop. We all have T flip-flop truth table. So if you observe T flip-flop truth table, I am using a small rough portion to show you T flip-flop truth table. In case if the clock level is low, then irrespective of the data applied to T, your state of Qn plus 1 will remain in Qn. In case if the clock is high, then for T is equals to 0, it holds, and for T is equals to 1, it toggles. Okay? Yes sir. Now please observe, since here we have Q0 as an input to T1. So Q1 toggles only when T1 is 1. T1 is 1 means Q0 is 1 and a clock is applied. So Q1 toggles only when Q0 is 1 and clock is applied. If we talk about Q2, clock applied, clock is a edge triggered. It means whenever there is a transition of the clock from 0 to 1. Clock applied means the transition of the clock from 0 to 1. Is it okay? Yes sir. Q2 toggles only when T2 is 1. T2 is 1 when the output of this AND gate is high, and output of this AND gate is high when Q1 and Q0 both are high. So when Q1 and Q0 are high, toggles only when the product of Q1 Q0 is 1 and clock is applied. Is it okay? Yes sir. In the same way, Q3 toggles only when T3 is high and a clock is in transition from 1 to 0. It means clock is applied. T3 is high when Q0 is high, Q1 is high and Q2 is high. The product of Q0, Q1 and operation of Q0, Q1 and Q2 and a clock is applied. How many of you able to understand the way which we can opt for the observation of the circuit? Is it okay? Yes sir. Now let's see whether it is acting as a series, whether it is acting as a up counter or not. That we can see with the help of truth table. So I am using truth table. Please observe clock, and we have a data Q3, Q2, Q1 and Q3, Q2, Q1 and Q0. Okay? Yes sir. On the 0th clock pulse, it means when there is no clock applied, circuit is in the initial state. If the initial state is not given to you, you have to consider it as 0, 0, 0, 0. Is it okay? Yes sir. Now whenever the clock is in transition, okay? Yes sir. And so on. Whenever the clock is in transition, your Q0 toggles. So Q0 toggles on every positive edge triggered clock. It means it changes its level on every next clock pulse. Is it okay? Yes sir. Q1 toggles only when Q0 is 1 and a clock is applied. Here Q0 is 0 and a clock is applied, so it will not toggle. Here Q0 is 1 and a clock is applied, so it toggles. Here 0 and a clock is applied, third clock, so it will not toggle, it will remain in its previous state, which is 1. Okay? Yes sir. Then If the Q0 is 1 and a fourth clock applied, then it toggles. How many of you able to understand up to this part, beta ji? So same goes on. Is it okay? Yes, sir. Now, if you observe for Q2, Q2 toggles only when Q1 into Q0 is 1. So please observe here Q2 into Q1 is 0, clock applied, so it will remain in the same state. Here if you observe Q2 into Q1 into Q0 is 1 into 1, that is 1, and a fourth clock is applied, so it will become logic 1. Again, until unless both Q1 and Q0 are high, it will remain in the previous state. Only when Q1 and Q0 both will become high, it toggles. So how many of you able to understand the observation now? Great. Can you observe for Q3? Q3 high toggles when Q2.Q1.Q0 is high and a clock is applied. So Q3 is high when Q1.Q2.Q0 is high. If any one of them is 0, then Q1.Q2.Q0 is a 0. So when the clock is applied, it will remain in the same state. Why? Because T3 is 0. Until unless T3 is 1 and a clock is applied, there is no change in the output state. If you observe, it will remain same up to this. At this, what happened? On the 7th clock, this will become high, this will become high, this will become high. When Q2, Q1 and Q0 all are high, it means T3 is high. Now, if 8th clock is applied, it will become logic level 1 and will remain 1 until unless Q2, Q1, Q0 will again become high. So we are getting binary of 0 to 15. On the 16th clock pulse, you will again get 0, 0, 0 only. So this is your mod 16 counter. How many of you able to understand this? Great, sir. How many of you able to understand it? Whenever we have to identify the number of different states, we always use to count the number of different states after applying the clock pulse. So we have total 16 states. So this is your mod 16 up counter. Mod 16 up counter. Is it okay? Yes, sir. One very important thing. We can design mod 16 up counter by using ripple counter as well. And we can design mod 16 up counter by using synchronous counter. So which one is better? In both we are using T flip-flop. 4 flip-flops we are using for 4-bit. So which one is better? If you remember, in case of a ripple counter, there is a problem of decoding error. And also the time period of the clock required will be greater than or equals to n TPDFF for n flip-flop. It means for 4 flip-flop, we need 4 TPDFF. Is it okay? But here, if you observe how much time period of the clock is needed, we can reduce the width of the, we can reduce the time period of the clock, and with the reduction of time period of the clock, you can say, sir, your speed of the counter increases. If you observe here, how much time is needed? All the flip-flop will operate at the same time. Yes, sir. And this AND gate should operate. Let us suppose the delay of this AND gate is TPD and the TPD AND. So it means 2 TPD of AND gate, and each will have the propagation delay of TPDFF. Each flip-flop will have a propagation delay of TPDFF. So all flip-flops will operate at the same time. Yes, sir. But this AND gate, it's a parallel carry up counter. I made a parallel carry up counter. It's a parallel carry up counter, beta ji. Kindly do a correction here. I have made a parallel carry up counter. This is a parallel carry up counter. None of you are giving the answer. So kindly correct it. This is the parallel carry up counter. Now all the AND gates are going to operate at the same time. If all the AND gates are going to operate at the same time, then how much time required? Sir, time period of the clock TCLK must be greater than or equals to TPDFF plus TPD of AND gate. Is it okay? So this is the best counter. What is the difference between series and parallel carry up counter? If we talk about series carry up counter, in that the AND gate output is connected to the next AND gate input. So this AND gate will operate only when this AND gate will operate in case of series carry up counter. So what is the difference between series and parallel? Please observe. Presently what I am showing is a parallel carry up counter. If we talk about series, so series carry up counter will be like this. Series carry up counter will be like this. Series carry up counter will be like this. This is your series carry up counter. If we talk about series carry up counter, it will be like this. And for that, the time period will become, for that time period will become, here we have to use n minus 2 TPD of AND gate. Because first two don't need AND gate, rest all AND gates are needed. First two don't need AND gate, rest any number of bits needed AND gate, and the output of one AND gate is connected to the input of other AND gate. So the speed is slower. If you want to improve the speed, we can go with a parallel carry up counter. In case of parallel carry up counter, speed increases. Why? Because all the AND gates are going to operate parallelly. So now I am going to make a parallel carry up counter again. Please observe. In case of parallel carry up counter, which we have drawn earlier, so this is your parallel carry up counter. In case of parallel carry up counter, this is not needed. Now all the AND gates are going to operate at the same time. So the basic difference between series and parallel carry up counter, I am hoping all of you able to understand. Is it okay? So if we want to design a series carry up counter, if we want to design a synchronous up counter, the best is to go with a synchronous parallel carry up counter. Is it okay? How many of you able to understand? The same circuit can be used for the designing of carry down counter as well. For that we have to use Q complement as the input to the next flip flops. Is it okay? So please observe down counter as well. Please observe the down counter as well. How many of you able to understand, Betaji? Please let me know by writing in the comment section. There is a small correction. The present circuit is a parallel carry up counter. For series carry up counter, you have to connect the AND gate output of this with the AND gate output of next. Is it okay? However, we will not prefer a series carry up. Why? Because there is a delay in the series carry up. It will be better to go with a parallel carry up counter. Hoping all of you able to understand up to this part. Yes, sir. Same, if we talk about synchronous series carry down counter, then for down counter, I am using 4-bit down counter. Please observe, Betaji. Synchronous series carry down counter. First observe synchronous series carry down counter. In the same, I will show you the parallel carry down counter as well. So we have T0, Q0, Q0 complement. If we make T0 as a Q0 complement as an input to T1, Q1, Q1 complement. Okay. You are using AND gate with these two inputs to T2. So this is what we called synchronous. Here this T0 is 1. Okay. So it toggles on every positive edge triggered clock. However, it will toggle only when Q0 is 0 or Q0 bar is 1 and a clock is applied. Same clock is applied to all flip flops. Is it okay, Betaji? Please let me know by writing in the comment section, Betaji. Someone is asking, sir, my goal is MTech Power Electronics, but financially tough. Okay. See, beta ji, in case if you find that you have to support your family first, then first of all you have to make your goal towards PSUs, public sector units, okay, through GATE or direct recruitment. Like some of the PSUs are taking the recruitment directly, okay. So you can fill the form of those as well. The same GATE preparation is going to help you for the same, for any PSU, okay. So you can target PSU as your first choice, and for that you have to score in GATE 200 rank, okay. If you are below 200 rank, it means below 200 is very good, very high chances. Up to 200 you have an opportunity to go in the PSUs through GATE, okay. Or if you are getting up to this rank now, you can easily crack any other state level PSU exam as well, okay, with the same preparation. So you can aim first for the PSU, okay, so that you can have support, and you can do your MTech as per your desire. You want to do the power electronics MTech, so you can do it later on. There is no issue. Now please observe, come back to this. Many students are using the same way, okay. So they first do the jobs in PSU, they will gather some money, and then they start doing their higher studies, okay. You can also have an opportunity to do MTech through PSUs, okay. A lot of PSUs are giving you an opportunity to do MTech on, they will give you all the finance support, okay, and the leave as well. But for that you have to follow the minimum criteria of serving years. After MTech you have to serve some particular period in the same PSU, okay. Now please see Q0, Q1, Q2 and Q3. Already I have already shown to you. This is not a better one. Why? Because in this case we need a clock must be greater than or equals to TPD-FF plus n minus 2 TPD of AND gate, where n is the number of bits. If you want to design a 4-bit synchronous carry up, synchronous series carry down counter, then you can put n is equals to 4. Is it okay? So 2 AND gate. But instead of using this, if we go with the parallel, then we need not to wait this AND gate to operate. We need not to wait for this AND gate to operate. Is it okay? We need not to wait for this AND gate to operate, because all the AND gates are going to operate parallelly and your circuit will become faster. If the clock time period reduces, it means your counter is becoming faster. How many of you able to understand up to this part, beta ji? So we generally use synchronous parallel carry up or carry down counter. They are much faster than series carry up or carry down, and much faster comparative to ripple up or down counters. Is it okay? Great, sir. Now please observe, next I am moving towards ring counter. Next, write down ring counter. So ring counter is basically a shift resistor. Ring counter is basically a shift resistor. A ring counter is also a synchronous counter only. Ring counter is a shift register in which last flip-flop output is connected to first flip-flop input. First flip-flop input. Ring counter is highly used in the automation industries, especially in the manufacturing units, automated manufacturing units, where we are using stepper motors to perform their work, and stepper motors are commanded by the ring counters. Is it okay? Yes, sir. So if we talk about ring counter, then ring counter can be designed by using JK or D flip-flop. We will prefer to design it by using JK flip-flop because shift resistors are generally designed by using JK flip-flop. Now please observe JKQQ bar, JKQQ bar, JKQQ bar, JKQQ bar. See, in this, outputs of one flip-flop is connected to another flip-flop, and last outputs are connected to first. So that is why it is called as a ring counter. In a ring counter, all flip-flops, because it is a synchronous counter, so all flip-flops are connected with the same clock. All flip-flops are connected with the same clock. Is it okay? Yes, sir. Here we can consider this as a MSB. Next significant bit, just for understanding. However, in synchronous counters, until unless designer will define the MSB and LSB, you can't identify by yourself which one is MSB and which one is LSB. Is it okay? Yes, sir. Now this is a ring counter by using JK flip-flop. We all know if the two flip-flops are cascaded with the outputs connected to the input of next JK flip-flop, then these two JK flip-flops are similar to the D flip-flop, because here the data is just going to shift from Q3 to Q2, Q2 to Q1, Q1 to Q0, and Q0 again shifted back to Q3. Is it okay? Yes, sir. So it can also be designed by using D flip-flop. If we observe by using D flip-flop, ring counter, 4-bit ring counter by using D flip-flop. Please observe, beta ji. We have D, Q, Q bar, D, Q, Q bar, D, Q, Q bar, D, Q, Q bar. So all are connected with the same clock. It means all will get activated at the same time, and last flip-flop output is connected to the first flip-flop input. Is it okay? Yes, sir. This is D3, Q3, Q3 complement, D2, Q2, Q2 complement, D1, Q1, Q1 complement, D0, Q0, Q0 complement. Okay? Yes, sir. How it work? Sir, it is very simple. It's just a simple shift resistor where Q3 is going to be shifted to Q2 and Q2 is going to be shifted to Q1. Q1 is going to be shifted to Q0 on application of the clocks, and Q0 is connected to D3. Is it okay? Yes, sir. So on 0th clock pulse, if we consider initial state to be 0, 0, 0, 1, in the ring counter, only one flip-flop output is 1, remaining are 0. Okay. Then on the first clock, what happened? This one will take Q3 position. This will be shifted here. This will be shifted here. This will be shifted here. In the next clock pulse, what happened? In the next clock pulse, this is 0 shifted here. This 1 is shifted here. This 0 is shifted here. This 0 is shifted here. We all have studied about the shift resistor. Okay. So this 0 again. This 0 is shifted here. This 1 is shifted here. This 0 is shifted here. On to the fourth clock, what happened? 0, 0. I'm sorry for this. This is 0 na? 0 and 1. So how many number of different states in a ring counter? For a 4-bit ring counter, we have only 4 states. For a 4-bit ring counter, we have only 4 states. And if you observe, if on the first clock pulse we are getting Q3 high, then on the 4th clock pulse, on the 5th clock pulse again we are getting Q3 high. So time period of the Q3 is 4 clock cycles. Is it okay? So we all can see that if the clock frequency is FCLK, then FCLK by 4, FCLK by 4, FCLK by 4 and FCLK by 4. It means output frequency at any output is equals to FCLK by 4 only. Is it okay? Because on after every fourth clock pulse, we are getting the same condition of each of the flip-flops output. Is it okay? So it means 4 clock cycles. After 4 clock cycles, the output will have one complete cycle. Is it okay? Please let me know by writing in the comment section, beta ji. Great, sir. Now please observe. How many number of unused state in a ring counter? If we talk about ring counter, the number of unused state in a ring counter. Number of unused state in n-bit ring counter. With the n-bit, how many total number of states possible? 2 to the power n. With the n-bit total number of state possible, 2 to the power n. Out of which we have n state valid, n valid state. So the number of unused state in a ring counter, is equals to 2 to the power n whole minus n. Suppose if we have 4 bit, then 2 to the power 4, 16 combinations are possible from binary of 0 to binary of 16. Binary of 15. Binary of 0 to binary of 15. We have total 16 combination possible. Out of 16 possible combination, we have a 4 combination valid for this ring counter. Ring counter will have only 4 used state for a 4 bit. So how many number of unused state? 12 number of unused state for a 4 bit ring counter. Similarly, for a n bit, you can find out 2 to the power n whole minus n. Is it okay, beta ji? Please let me know by writing in the comment section. Applications. So mostly used in analog to digital converters, in digital clocks, frequency counters and stepper motor. Mostly stepper motors are being controlled by using ring counter. How many of you able to understand ring counter? The question arises in our mind, sir, how we will make one of the output high? It is quite difficult. Yes. So can we design a ring counter? Which will start by itself? Yes, it means if initially all the flip-flops are resetted, if we give first clock pulse, we will get this state. On second, we will get this state. Third, we will get this. Fourth, we will get this. Fifth, again, it will remain in these states. So initially, even if 0, 0, 0, the ring counter gets self-started. Can we design such a ring counter? Yes. So again, how to design? First, we have initial state 0, 0, 0. Then onto the application of the clock, next state is the binary of 8. Next state is the binary of 4. Next state is the binary of 2. Next state binary of 1. And next state binary of 8 again. Is it okay? So it will not come back to 0. Present state, next required state. Present state, next required state. Accordingly, you can construct the excitation table, minimize it and implement the logic circuit. When you do all these things, you can design a self-started ring counter. So please observe a self-started ring counter. In a self-started ring counter, we have D0, Q0, D3, Q3, Q3 complement, D2, Q2, Q2 complement, D1, Q1, Q1 complement, D0, Q0, Q0 complement. Now if you observe, we have a XNOR operation of Q3 plus Q2 plus Q1 complement. Is it okay? Yes, sir. This is your self-started ring counter. At the time of start, if all the flip-flops are resetted to 0, then 0 XOR 0 XOR 0, 0 plus 0 plus 0, 0, whole complement is logic level 1. So D3 will become 1. And this 0 will shifted here, this 0 will shifted here, this 0 will shifted here. On application of the first clock pulse, Q3 will become high. If Q3 is high or Q2 is high or Q1 is high, any one of them is high, then output of XNOR gate is logic 0. Is it okay? So automatically it will work for the 4 clock pulses, and then on the 5th clock pulse again the same condition is going to repeat. Is it okay? So this will be a self-started ring counter. How many of you able to understand, beta ji? Please let me know by writing the comment section. Great, sir. Self-started ring counter. Now let's talk about Johnson ring counter. Johnson ring counter, also called as twisted ring counter, sometime also called as creeping counter, switch tail counter, walking counter, or Mobius counter. All are the name of the Johnson counter only. So in a Johnson counter, twisted ring counter, the complement of the output of last bit is shifted to first bit of the shift register. So how it would work? It would work like this. We have a shift register. We have a shift register. Yes, sir. And in the shift register, the last flip-flop output is inverted and connected to the first flip-flop input. Is it okay? Great, sir. Suppose if I design for 3-bit, then what are the different possible states of Q3, Q2, Q1 and or Q1, Q2, Q1 and Q0. So we all can see, sir, initially if on 0th clock pulse, if we have the state 0, 0, 0, then on application of the first clock pulse, we get the state 1, 0, 0. On application of second clock pulse, we have the state 1, 1, 0. This it's complemented, and on application of third clock, we have 1, 1, 1, because these are going to be shifted. It is a shift register only with the output of last flip-flop complemented and connected to the first flip-flop input. Now, on application of 4th clock pulse, you will get 0, 1, 1. On application of 5th clock pulse, you will get 0, 0, 1. On application of 6th clock pulse, you will get 0, 0, 0. So how many number of different states? We have 6 different states for 3-bit. Is it okay? Yes, sir. So we want to design a Johnson ring counter, a twisted ring counter. In a ring counter, the last flip-flop is connected to the first flip-flop input. In a twisted ring counter, the last flip-flop output is twisted and connected to the first flip-flop input. We can design this twisted ring counter either by using JK flip-flop or by using D flip-flop. Let me show you both. So 3-bit Johnson ring counter by using JK flip-flop, or 3-bit Johnson ring counter by using D flip-flop. Please observe, beta ji, if you are using JK, then twisted ring counter is like this. You can choose any one of them as a MSB or any one of them as a LSB, because for synchronous sequential circuits, designer need to define the MSBs or LSBs. Okay? Yes, sir. It can also be represented by using D flip-flop, because JK flip-flop and D flip-flop, if you compare, then if Q is the input to J, then Q bar is the input to K, and that will become a D flip-flop. Is it okay? We all know about D flip-flop. D flip-flop is designed by using JK flip-flop. So JK, even if we are going to represent like this, it will become D flip-flop. Is it okay? So we all know about D flip-flop. So can I represent it by a D flip-flop? Yes, sir. D Q Q Q bar, D Q Q bar, where the output, this one is connected with the input, and these are being shifted. All are connected with the same clock. How many of you able to understand, beta ji? So this is your twisted ring counter by using JK flip-flop or by using D flip-flop. I have made a 3-bit Johnson ring counter. Similarly, for 4-bit, you can increase one more flip-flops and so on. Is it okay? Great, sir. How many of you able to understand up to this part? Now, one demerit of Johnson ring counter is lockout, and during lockout your counter may present in some unused state, so it will not return back to its characteristic even if you are going to apply the clocks again and again, and that happened because of the different propagation delays of the different flip-flops. Is it okay? Yes, sir. Now if you talk about how many number of states, for 3-bit we have 6 state. In the same way, if you observe for 4-bit we have 8 state. It means Johnson ring counter, how many number of states are there? Sir, 2 into n. Number of states used in twisted ring counter is equals to 2 into n. If we talk about frequency, then frequency of output at any output, either Q2 or Q1 or Q0, if you observe, the frequency is FCLK by M. M is the number of different states. Here we have 2n. Is it okay? Yes, sir. Only one demerit. So, during lockout, counter may present in unused state. During lockout, counter may present in unused state. Is it okay? Great, sir. Let's have one question to understand the lockout as well. Suppose consider twisted ring counter shown below. I know I am moving little bit faster because I have to cover many things. Okay. But since it's a live class, so wherever you want to note down, you can just pause and note down and then you can go ahead. Okay. Now please observe here. In a twisted ring counter, consider a twisted ring counter shown below. Suppose if we have a twisted ring counter this, I am using JK flip-flop. Having clock frequency FCLK. If the clock frequency is FCLK and the initial state is also given to you 1, 0, 1. This initial state is also given to you. Okay, 1, 0, 1. Initial state is also given to you. The output frequency at output Z is, here you have the output Z. So can you tell me whether it will be FCLK by 2, FCLK by 6, FCLK by 4 or FCL by 8. Can you tell me what is the output frequency in case of a twisted ring counter with the initial condition given? This condition may occur because of some propagation delay of the flip-flops. Different flip-flops may have different propagation delay, and there is a possibility that if the clock level is not properly chosen, if the clock time period is not properly chosen, there is a probability that the output will come in this condition. So what happened if the output will come in this condition? Now please observe, beta ji. As per the formula, you can answer, sir, we have a Johnson ring counter, 3 flip-flops, so 2 into n number of states, so output frequency is FCLK by m. Absolutely right, FCLK by m is your output frequency, where m is the number of different state. But how many number of different state in this case? Because here initial condition is given to you. Let me assume it Q2, Q1 and Q0. Okay, I am doing the solution part. Please observe. And we have a clock. Initially, suppose on 0th clock pulse, we have given the state as 101. So what happened on the second clock? We all know this is a Johnson ring counter. The Johnson ring counter will have a circuit equivalent to this circuit. Yes, sir. So here Q2 data is going to be shifted to Q1 and Q1 data is going to be shifted to Q0. Q0 complement data is again going to be shifted to Q2. So if you observe, this Q0 complement will become 0, 1. Q0 is 1, so its complement will become on the first clock pulse. On the first clock pulse, what happened? On first clock pulse, this will become 1. This 1 is shifted here, this 0 is shifted here. On second clock pulse, what happened? This will become 1. This 0 is shifted here, this 1 is shifted here. So it doesn't matter how many clock pulses you are going to put. For n number of clock pulses, you have only 2 states. So if only 2 states, then the output frequency will become FCLK by m. So output frequency will become FCLK by m. Here m is only 2 because your counter is in lockout state. It will not return back to its original state, and 101 or 010 is not the used state in a Johnson ring counter. If you observe the used state in a Johnson ring counter, we don't get 010 or 101. Is it okay? So because of the propagation delay, your Johnson ring counter may goes into unused state and there it would get logged out. How many of you able to understand this? Great. So the correct answer is this, not this. If the initial conditions are not given, then we can say FCLK by 6. Hoping all of you able to understand this. Great. Please let me know by writing in the comment section, beta ji. If you have any doubt, please let me know by writing in the comment section. Great. Now please observe here. We can also design a non-binary synchronous counters. While designing non-binary synchronous counters, again we will use the concept of preset and set, which will be indicated as clear or preset. Is it okay? Sometimes a bar is present just before the clear pin and then it will become clear bar. Very similar to the one we have studied in the ripple counter, non-binary ripple counter. Is it okay? So we have a mod n counter using synchronous binary up counter. We have here a synchronous binary up counter. Is it okay? Yes, sir. With a synchronous clear input. See, 2 types of clear pin we have. Asynchronous clear pin is used in asynchronous counters where the condition appeared, the outputs will get cleared of every flip-flop. In case of asynchronous flip-flops, whenever condition appeared, irrespective whether the clock appear or not, all the flip-flops are resetted. Is it okay? However, in case of synchronous clear pin, the clear pin is synchronized with the clock. So when the clear condition appear and a clock is applied, then only in synchronous counter all the flip-flops get cleared. Is it okay? Yes, sir. You have to find out the value of mod n. Now please observe here. We are using binary up counter. So this is a binary up counter. Is it okay? Yes, sir. So we have QA, QB, QC and QD. Is it okay? And the initial state is 0 0 0 you can consider. So considering on the 0th clock pulse, the state is 0 0 0 0 of all the flip-flops. We know about the synchronous parallel carry up counter. So inside this circuit, we have a synchronous parallel carry up counter. Okay. With each of the flip-flops are connected with a clear pin. The counter get cleared. It means all the flip-flops of the counters states will be resetted to 0 if 0 input is appeared on this pin. This pin is the output of NAND gate. So whenever output of NAND will become 0, your output of the synchronous counter will be 0 0 0. No sir, condition appear. When clock appear along with the condition, then only it cleared. Is it okay? Yes sir. Now please observe that this is the basic difference between the synchronous clear pin and asynchronous clear pin. Is it okay? Yes sir. Now please observe. On first clock what happened? We will get the binary of 1. This is a NAND gate. NAND gate output is logic 0 when both the input of NAND gates are 1 1. Both the input means QC and QB. When QC and QB first time will become 1 1, then only your clear condition appear. So in this no clear condition appear, so clear pin will not activated, and in the next clock pulse it will become 0 0 1 0. In the same way we will get from the third clock pulse 0 0 1 1. In the fourth clock pulse also we are getting 0 1 0 1 as a stable states. These are all stable states because your clear condition is not appearing. However, on the sixth clock pulse your clear condition get appeared. If this counter is a asynchronous counter and with a asynchronous clear pin, then instead of getting this condition, we would get 0 0 0. But this is a synchronous clear pin and it is a synchronous counter. So under this condition, we have we can see that onto the sixth clock pulse, reset condition appeared onto the clear pin. But your flip-flop will not cleared, it will get cleared on the 7th clock. Is it okay? Yes sir. Because in case of a synchronous clear pin, when clear condition appeared and a clock is applied, then only the flip-flops get cleared. Is it okay? When it's resetted to 0. So how many number of different states we have? It will be counted after first clock pulse. So after first clock pulse, if you observe, how many number of different states? 1, 2, 3, 4, 5, 6, 7. So we have 7 states. So 7 state means this is a mod 7 counter. Mod 7 counter. How many of you able to understand? Don't write it mod 6 counter. This is your mod 7. If the counter is a asynchronous counter and a asynchronous reset pin is there, then mod 6 counter. Is it okay? In case of synchronous clear pin, the counter clears all the flip-flops only when the condition appeared and a clock is applied. Is it okay, beta ji? Hoping all of you able to understand up to this part perfectly. Great. Hoping all of you able to understand up to this part perfectly. Please let me know by writing the comment section. I am using the same question once again to make you understand the topic perfectly. Suppose if this, I am modifying the question little bit, keeping everything same. Okay, this is a up counter only. I am modifying little bit. Hoping all of you able to understand this one. Why it is called as a mod 7? We have 7 different state. First clock, second clock, third clock, fourth clock, fifth clock, sixth clock, seventh clock. 0 0 0 is also a state. Is it okay? Now please observe. Suppose if we have a mod n, by using asynchronous counter, binary up counter, by using asynchronous binary up counter with a asynchronous clear input pin. Then if this is a asynchronous binary up counter, okay, it can be a ripple counter or anything, then on the 7th clock pulse we will not get the 7th clock. Why? Because onto the binary condition of 0 1 1 0, onto the binary condition of 6 we are getting clear condition. So instead of getting this state, we would get 0 0 0 0. So how many number of different state we have? Only 6 state we have. Is it okay? So the basic difference between asynchronous clear pin and synchronous clear pin, hoping all of you able to understand. Is it okay, beta ji? Please let me know by writing in the comment section. Great. So I am keeping these two. Now you would have 6 states only. So the basic difference between the asynchronous clear input pin and synchronous clear input pin is now. Hoping all of you got clarity on this. Great. Next, write down finite state. That's all about your synchronous counter. So now we know about the asynchronous counters, ripple counters, how to design ripple counters, what should be the time period of the clock for satisfactory operation, decoding error, and also we have observed synchronous counter, how to design desired synchronous counter. We know about the steps to design desired synchronous counter, synchronous series or parallel carry up, synchronous series or parallel carry down counter, time period of the clock needed, why they are faster comparative to the synchronous counter, and also we have observed ring counter and Johnson ring counter. Is it okay? And we have seen lockout may occur in the Johnson ring counter. So these are the important things that you have to remember up to the lecture completed. Is it okay? Next, write down finite state machine. So now I am approaching towards today's part. Please let me know by writing in the comment section, beta ji, all of you able to understand up to the part completed. Can you please let me know by writing in the comment section, all of you able to understand up to the part completed? Great. See, next is your finite state machine. Very, very important for electronics, electrical. Okay. And if we talk about CS, then it is very important because sequence detector is very important part of your syllabus. Sequence detector. You can understand how to design a sequence detector by understanding the finite state machine only. Now let's talk about finite state machine. See, we have seen counters. So in a counters, you can design a desired number of states and you can design a desired counter, synchronous counters. You can design a desired synchronous counters. If we talk about any kind of counter which will have finite number of state, then that counter comes under a finite state machine. Whenever we want to design any state machine, for different number of states, the number of flip-flops required change as per the relation m is less than or equals to 2 to the power n, where we all know m is the number of states and n is the number of flip-flops. So can you design an infinite state machine? It is not possible. Why? Because if you want to design infinite state machine, you need infinite number of flip-flops. So whatever state machines we are designing, all are finite state machines. Clocked synchronous sequential circuit categorized by two models. One is called as a Mealy model circuit, another one is called as a Moore model circuit. So if we talk about Mealy model circuit, Mealy model output is the function of present state only. Output is the function of present state and present input. I'm sorry. Output is the function of present state and present input. Present state and present input. If we talk about Moore model, so the difference between Moore and Mealy is, in Mealy model, output is the function of present input and present state. However, in case of a Moore model, output is the function of f is representing function. F means function of present state only. So output is the function of present state only in case of a Moore model. However, in case of a Mealy model, output is the function of present state as well as present input. Is it okay? This is the basic difference. Let's see the basic difference. Let's see the differences. So the basic difference is, Mealy model, output is the function of present input and present state. Moore model, output is the function of present state only. Whenever we want to design a circuit, we can either choose Mealy model or we can choose Moore model for a finite state machines. So if you want to design a finite state machine by using Mealy model, then number of states are less comparative to the Moore model. If the number of states are less, there is a possibility number of flip-flops required will be lower in case of Mealy model. So cost wise, you can say Mealy model is a little bit economical. But if we talk about circuit complexities, so circuit complexities wise, your Mealy model is more complex comparative to Moore model. Is it okay? Yes, sir. Now let's try to understand the Mealy and Moore model with the help of example. So I'm using one question first. We will discuss how to identify the output, how to design the state table, and then we will see state reduction technique and state diagram. Later on, we are going to design desired state model, you can say sequence detector, by using Mealy or Moore model. Is it okay? Yes, sir. So now please observe here. First, I am using one question. Can you please tell me whether this model is a Mealy model or a Moore model? Sir, as per the question, it is a Mealy model. It is mentioned. No, I just wanted to know how you can identify whether the given model is a Mealy model or a Moore model. For that, you have to observe the output. If you observe the output, output is the function of Q as well as X. It means present input and present state. If the output is the function of present input and present state, the model is said to be a Mealy model. Is it okay? Beta ji, it is coming very soon. Is it okay? Some 865 vacancies already announced. I think Tamil Nadu Power Corporation has announced this. So you can check out once. And if you are eligible, you can apply there. Okay. See, Betaji, all different state PSUs are conducting their exam apart from GATE. They have take a separate exam, but the exam level and the question they are going to ask is same as that of the GATE questions. Is it okay? They are little bit lower comparative to the GATE level. Okay, great. Is it okay up to this part? Transco vacancies are there, and Transco questions are almost similar. Transco, UPPCL, all are similar. So their question levels are a little bit lower than GATE, but all the GATE syllabus and Transco syllabus is almost same. Is it okay? Great. So Genco, Transco are same as your GATE level. If you are preparing for GATE, automatically all the entire technical subjects are covered. Okay, and you can easily appear in the exam. Rest of the eligibility criteria you can check, Betaji. Now please observe. So consider the given Mealy model sequential circuit. Consider the given Mealy model sequential circuit shown below. Derive the state table and state diagram. So First of all, we have to construct the state table, and then we need to draw the state diagram. Okay. Before approaching towards the solution part, first of all, we have to identify the inputs of the flip-flop. To solve any sequential circuit, it doesn't matter synchronous or asynchronous, to design solve any question based on the sequential circuit, you have to identify first inputs to the different flip-flop, then apply clock pulse and follow the truth table. Okay. So please observe here, what is the input to D1? Sir, we can observe the input to D1. Please observe, beta ji, input to D1, input to D1. So we have Q1 complement here, and Q1 complement is coming to this. Q1 complement is coming to this, as well as Q1 complement is coming to this. And we can see we have Q2 complement. Q2 complement is coming to this. Q2 complement. Yes, sir. We have X complement and X. Yes, sir. One more. If you observe this one, we have Q1, Q2 is coming to this. Is it okay? Yes, sir. So can you find out the input is coming to D? So the data coming to D is QX1 bar, Q2 bar plus of Q2, Q1 complement. Can I make like this? Yes, sir. So this is your D1. This is the data onto D1. Is it okay? This is the input to D1. Similarly, if you identify the input to D2, what is the input to D2? This is the clock. Okay. Input to D2. Input to D2 is, we have Q1 bar, Q2, Q1 bar, and X Q1 bar. So the data on D2 we have. Before applying clock pulse, first we need to find input to the different flip-flops. D1 we have X1 complement, Q2 complement plus of Q2, Q1 complement. Okay. And we have D2 data we have X Q1 complement plus of Q2, Q1 complement. And we can also see the output. What is the output? Let us suppose output is Z. So Z output is equals to X bar Q1, X bar Q1 plus of, we have X Q2 bar, Q1 bar, X Q2 bar, Q1 bar. How many of you can see the inputs to the different flip-flops as well as the output? Yes, sir. So first of all, you have to identify the input. First of all, you have to identify the input to the different flip-flops and output function as well. Is it okay? Beta ji, please observe up to this part. If there is any doubt, please let me know. Now we have D1. We have D1. So D1 is X1, X bar, Q2 bar, X bar, Q2 bar plus of Q1, Q2, Q1 bar, Q2, Q1 bar. Okay. D2 we have X Q1 bar. D2 we have X Q1 bar plus of Q2, Q1 bar. And output function Z we have X bar Q1, X bar Q1 plus of X Q2 bar Q1 bar, X Q2 bar Q1 bar. Is it okay, beta ji? Now please observe very carefully. I am going to design a state table now. So please observe state table. Please observe state table. In a state table, first of all, we have present state, present state, next state, output Z, output Z. Next state with x is equals to 1 or x is equals to 0. Since we have one input, so one input will have two possibility. If we have two input, we have four possibility. If we have three input, we have six possibility. Here we have one input x, so x input will have two possibilities. So I am taking both the possibilities as next state. At next state, is it okay? Yes, sir. Now output also depends upon the next state. So output with x is equals to 0 and x is equals to 1, and we have present state. So present state, next state, output Z. Now please observe, in terms of Q2 and Q1, in terms of Q2 and Q1, next state will become Q2 plus 1 and Q1 plus 1, Q2 plus 1 and Q1 plus 1, x is equals to 0 and x is equals to 1. So output Z with x is equals to 1 and x is equals to 0. Is it okay? Output with x is equals to 0, or let it be like this only. Output with x is equals to 0 and x is equals to 1. Now please observe, beta ji, Z. Now please observe, beta ji, what are the possibilities with the two bits? How many possibilities for the 2 bit? 4 possibilities. How many possibilities for the 2 bit? Sir, 4 possibilities. So if the present state is 0, 0, if the present state is 0, 0, maybe your present state is 0, 0, 0, 1, 1, 0, 1, 1. 4 states can be represented like this. So 0, 0, 0, 1, 1, 0 or 1, 1. Present state may be 0, 0, 0, 1, 1, 0 or 1, 1. So 4 possibility we have for the present state. Is it okay? Yes, sir. 4 possibility we have with the present state. Now I am interested with x is equals to 0 first. What happens to d2 with x is equals to 0? Please observe here. d2 with x equals to 0. With x is equals to 0, your d2 will become 0 q2 q1 complement. Is it okay? So with x is equals to 0, your next state, because D flip-flop, we all know about the truth table of D flip-flop. In a D flip-flop, we all know about the truth table of D flip-flop. If we apply 0, we get 0. If we apply 1, we get 1. We all know about the truth table of the D flip-flop. Before applying clock pulse, first find input to the flip-flop. So now we know about the D2. D2 is Q2 Q1 complement. Q2 Q1 complement. So if Q2 Q1 complement is logic level 1 with x is equals to 0, you will get next state of Q2 plus 1. Is it okay? Yes, sir. So please observe, with x is equals to 0, if we have Q2 0, Q1 0, present state 0, 0, then what happened to the next state Q2 plus 1? If x is equals to 0, this 1, 0, only on 1, 0, d2 is high. Rest everywhere d2 is low. So if d2 is low, your next state Q2 plus 1 will remain low. Only at 1, 0, it will be high. Is it okay? Yes, sir. Now with x is equals to 0, d2 with x is equals to 1. With x is equals to 1. If we talk about d2 with x is equals to 1, then what is your d2? d2 will become q1 complement, because if you take q1 complement common, then 1 plus q2 is reduces to 1 only. So q1 complement. So whenever q1 is 0, its complement is high. So with x is equals to 1, your next state of the flip-flop 2 will become high when q1 is low. When it is high, yes, sir. How many of you able to understand? In the same way, you can observe for D1. You can observe for D1. D1 with x is equals to 0. If you observe D1 with x is equals to 0, you will get D1 to be equals to Q2 complement plus of Q2 Q1 complement, which can be further by using distribution theorem. You can write Q2 bar plus Q2 dot Q2 bar plus Q1 bar. So Q2 bar plus Q1 bar. Is it okay? That indicates Q2 Q1 whole complement. Is it okay? Yes, sir. So if any one of them is low, your D1 is high. If any one of them is low, your D1 is high, and on application of the clock, your Q1 plus 1 will become high. If any one of them is low, this will be high. Only when both are 1, 1, then this will become 0, because it is a NAND, Q2 dot Q1 whole complement. Is it okay, beta ji? Can I write like this? I can treat it as distribution theorem, 1, 2, 3, 1 plus 2, 1 plus 3. So 1 plus 2 logic level 1 only, and we have Q2 bar plus Q1 complement. With x is equals to D1 with x equals to logic level 1. This will become 0, and D1 will become Q2 Q1 complement. So Q2 Q1 complement is high only at this position. Rest everywhere you will get 0. How many of you able to understand, beta ji? Now talk about output. Again, output Z is equals to x bar Q1 plus of x Q2 bar Q1 bar. So in case if x is equals to 0, what you will get? In case if x is equals to 0, we get Q1 only. Because x is 0, so this will be 0, and x is 0, 0 bar 1 into Q1 only. So if Q1 is high, we get high with x is equals to 0. If Q1 is low, we get low. Okay? Yes, sir. With x is equals to 1, this will become 0. You have to observe Q2 bar Q1 bar. Q2 bar Q1 bar is high only at this. Rest everywhere, it will be low. How many of you now able to understand how to fill this state table? So from the circuit, first of all, I have identified the inputs. Then find the inputs to the flip-flop before applying clock pulse, and then apply clock pulse and follow the truth table. Because we have a 2 flip-flops, so how many possible states we have? 4 states possible. Either the present state 0, 0, 1, 0, 1, 1, 0, 1, 1, 0 or 1, 1. Is it okay? Now I am going to modify this state table to draw a state diagram. Please observe here. I am going to modify this state table to I am going to modify this state table for state diagram. Please observe here. So Q2 Q1, I am going to assign these as a states. Q2 Q1 can be assigned as a state A. So we have basically Q2 Q1. So Q2 Q1, I am assigning them as a state. Like 0, 0 I am assigning as a state A, 0, 1 I am assigning as a state B, 1, 0 I am assigning as a state C, 1, 1 I am assigning as a state D. Is it okay? Yes, sir. Now please observe, beta ji. If present state is A, 0, 0, if present state is A, 0, 0, if present state is A, 0, 0, then with x is equals to 0, next state will become 0, 1. And 0, 1 is your state B. So we are getting state B. And what is the output, beta ji? For a present state 0, 0, what is the output? For a present state 0, 0, with x is equals to 0, next state 0, 1, that is the state B, and output we are getting 0. So I am representing here output 0. Is it okay? Yes, sir. Again observe. Present state 0, 0, with x is equals to 1, next state 1, 0. 1, 0 is a state C. Is it okay? Yes, sir. And output 1. So present state A with x is equals to 1, next state will become C, output 1. How many of you able to understand this modified state table? Again observe present state 0, 1, present state 0, 1. So here we have a present state 0, 1 with x is equals to 0, next state 0, 1. It means if the present state is B with x is equals to 0, we are again getting state B and output 1. So we are getting state B and output 1. If present state is 0, 1, if present state is 0, 1 with x is equals to 1, next state we are getting A and output 0. Next state we are getting A, output 0. Next state we are getting A, output 0. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. Great. Present state C, present state C, present state C with x is equals to 0, next state D, output 0. Present state C, x is equals to 0, next state D, output 0. Next state D, output 0. Present state C, present state C with x is equals to 1, next state D, output 0. Present state C, x is equals to 1, next state D, output 0. So D 0, D 0. Present state D with x is equals to present state D, present state D with x is equals to 0, next state A, output 1. Next state A, output 1. Next state A, output 1. Present state D, x is equals to 1, next state A, output 0. Next state A, output 0. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. How many of you able to understand up to this part? Please let me know by writing in the comment section. Great. Yes, sir. Now we have a modified state table. We can use this state table to construct our state diagram. So we can construct state diagram. Please observe, beta ji. With this modified state table, we can have a state diagram. Now we have 4 states. So we have state A, state B, state C, and state D. Okay. Yes, sir. I'm using the capital D, na? Okay, sir. Now, if we are on state A, then with the input x is equals to 0, next state will become, with the input x is equals to 0, next state will become B and output will become 0. Arrow indicates going towards next state in the state diagram. First of the oblique indicate, or numerator part of this indicates input, and denominator part of this indicate output. This indicate present state. So this is your present state. Present state. Arrow indicates going towards next state. This is your present input. Present input, and this is your output. So if you are on state A, and input x is equals to 0, then next state will become B and output 0. If you are on state A, and x is equals to 1 appear, then next state is a C. Next state is a C and output 1. Is it okay? Yes, sir. If you are on state A, if you are on state B, and x is equals to 0, then remain on state B. Remain on state B with the output 1. If you are on state B and x is equals to 1, return back to state A. Output 0. If you are on state C, x is equals to 0, move to state D, output 0. And if you are on state C, x is equals to 1, move to state D, output 0. If you are in state D, x is equals to 1, x is equals to 1, move to state x is equals to 0, move to state A and output 1. If you are in state D, x is equals to 1, output 0, then also you will move to state A only. So this is what we called a state diagram of Mealy model. In a Mealy model state diagram, output is the function of input. So whenever you are giving input, it goes to next state, which is indicated by the arrow. Is it okay? So actually, how we utilize how to design any desired state machine. To design any desired state machine, first of all, we understand the user desire and construct a state diagram. After this state diagram, we can construct a state table. From this state table, we can construct this state table, and this state table extended towards excitation table by the flip-flop with which we want to design. Is it okay? And then we write the excitation equation, minimize it, and then we implement our desired circuit. So this is the process to design any desired state machine. How many of you able to understand, Betaji? Great, sir. So whenever user comes and asks you to have a state machine, okay, so first of all, you have to understand the user desire. Like he is saying, we have a 4 condition. If this thing happened, then condition reaches to this. Let us suppose we are talking about a call operator. Okay, a call operator will have 4 different positions. So first of all, you have called and asked that you want to know about the credit card balance. So it will send to you state B. If you want to ask about credit card, if you have any discrepancy in your credit card statement, go to state C. So in that way, user will ask you to design a digital circuit, and first of all, you understand the user desire. Accordingly, you construct a state table. Then you minimize the state table by using state reduction technique. After that, you construct a state table, then write excitation equation from the state table depending upon present state and next required state with the present input. Then you can find excitation equation, minimize it, and implement our any desired state machine. How many of you now able to understand this part perfectly? Great, sir. Is it okay, Betaji? Is there any doubt up to this part? Then please let me know by writing in the comment section. Is there any doubt up to this part? Please let me know by writing in the comment section. Is it okay? Great. So now we know about the state model. Is it okay, Betaji? Please let me know by writing in the comment section up to this part. If there is any doubt up to this part, please let me know by writing in the comment section. Great. So let's move toward Moore model introduction as well. So we'll have the understanding of state diagram in the Mealy and Moore, and then I am moving towards the state reduction technique. Later on, we will move towards sequence detector. We will see what is overlapping sequence detector, non-overlapping sequence detector, and how to design any desired sequence detector by using Mealy or Moore model. Is it okay? Great. Hoping up to this part everything is clear. Now please observe this part. Can you tell me the state diagram of this model? First, identify whether the given state machine is a Mealy state machine or a Moore state machine. So how to identify the given state machine is a Mealy state machine or Moore state machine? You have to observe the output. If you observe the output y is the function of QA and y is the function of QB. It means only present state. Y is not the function of present input. It is only the function of present state. So this is a Moore model. Is it okay? Yes, sir. Now you know about this is a Moore model. Next is you have to identify the you have to draw the state diagram, and you need to write the state table of the given model. So how to write the state table? First of all, we need to write the state table. We will use modified state table to draw the state diagram. So please observe here. First of all, we need to identify the inputs to the different flip-flops. So we all know about JA. What is JA? JA is same as QB. We all can see JA is the same as QB. We all can see JA is the same as QB. JA is the same as QB. Yes, sir. And KA is the same as X bar QB. You can observe here JB is X bar and KB is X XOR QA. Is it okay? Yes, sir. Now we know about the inputs as well as we know about the output. Output is QA XOR QB. Yes, sir. Next is to construct a state table. So before solving any question, first of all, you have to identify the different inputs to the flip-flop. Then apply clock pulse and follow the truth table. Is it okay? Yes, sir. Now please observe here. I'm using a state table first. So we have JA in a JK flip-flop. We have JA as QB, JA as QB, and KA as X bar QB. Okay. Yes, sir. Next we have JB we have X bar, and KB we have X XOR QA. X XOR QA. Is it okay? Yes, sir. And we also know about the output. Output Y is QA XOR QB. So before applying clock pulse, first find input to the flip-flop. Now, state table. So in a state table, first we have to write present state, then next state with X is equals to 0. Since we have only one input, if we have two input, it will become X is equals to 0, XY 0, 0, 0, 1, 1, 0, 1, 1, 4 possibilities. So we have two possibility with X, and we have output. Output is not the function of X, so output only depends upon present state. Okay, so we have output, present state, next state. Now please observe here. So present state in terms of QA QB. So we have X is equals to 0, QA plus 1, QB plus 1, and with X is equals to 1, we have QA plus 1, next state of flip-flop A, next state of flip-flop B. Is it okay? And output. Yes, sir. Now please observe, beta ji, how many possibility of different states with the two flip-flop? 4 possibility, either 0, 0, 1, 0, 1, 0, 0, 1, 1, 0 or 1, 1. 4 possibilities, sir. Now please observe, I am interested to check the next state for each. Is it okay? Please observe, beta ji. I am interested to check Don't know what you are writing. Good evening, beta ji Mank. Con chapter. Okay. I think you want to ask which chapter or which subject. Next subject you want to ask, huh? Which subject or which chapter is going on? Digital electronics. Okay, now I am able to understand. Digital electronics and your finite state machine is going on. Okay. Now please observe here, beta ji. Present state QA, QB 0, 0, 0, 1, 1, 0, 1, 1. 4 possibilities. Now suppose if the present state is 0, 0, then what is the next state with X is equals to 0? If we talk about X is equals to 0, then what is the condition for JA and KA with x is equals to 0. JA will become QB only and KA will become QB only. What happens with x is equals to 1? With x is equals to 1, JA will become QB only and KA will become 0. In the same way, you can observe for the flip-flop B as well. With x is equals to 0, JB will become 1 and KB will become, we all know if one input of XOR gate is logic level 0, it will act as a buffer. So QA. And with x is equals to 1, JB will become 0 and KB will become QA complement as a inverter. Is it okay? Yes, sir. Output we all have y is equals to QA XOR QB. It is not depending upon the input x. So now please observe here, with the present state 0, 0, with x is equals to 0, JA is the same as QB. So QB is 0. Yes, sir. And KA is the same as QB. Is it okay? Yes, sir. So in a JK flip-flop, if we are getting 0, 0, we all know about the truth table of JK flip-flop. JK flip-flop will have a truth table. J, K, Q, N plus 1. We all know about JK flip-flop truth table. I am writing in the rough for you. So Qn 0, 1, Qn complement. Yes, sir. We all can see for 0, 0, for 0, 0, JA 0, KA 0. For 0, 0, what happened? For 0, 0, your flip-flop A will remain in Qn state. What is the Qn state? 0. So your flip-flop A will remain in state 0. For 0, 1, what happened? For 0, 1, they are 1, 1. 1, 1 means it is going in toggle mode. So if previously 0 toggles to 1. For 1, 0, remain in the same state, because if QB is 0, then we are getting 0, 0. For 0, 0, it will remain in the hold state. For 1, 1, it goes in the toggle state. Yes, sir. So here it will remain 1. QA will remain 1. Hold. If QB is 1, then 1, 1 is getting onto the JAKA. So it toggles. If previously 1, it toggles to 0. Hoping all of you able to understand. Great. In the same fashion, you can find out for x is equals to 1 as well. What happened for x is equals to 1? For x is equals to 1, KA is 0 and JA is QB. So QB is 0. So 0, 0, 0, 0 hold state. If QB is 1, then we are getting 1, 0. For 1, 0, it will be in the set position. For QB 0, it will be remain in the hold state. And for QB 1, we are getting 1, 0. 1, 0 is a set state. So it will be in the set state. How many of you able to understand? Great. Now in the same way, observe for QB plus 1. How to identify for QB plus 1 with x is equals to 0? With x is equals to 0, JB is 1 and KB is QA. So KB is QA, QA is 0. So we are getting 1, 0 with x is equals to 0. 1, 0, 1, 0 is a set. 1, 0 is a set. 1, 0 is a set. So we are getting set. Now with QA 0, 1, 0, 1, 0 is a set. With QA 1, 1, 1, 1, 1 is a toggle state. Toggle state means if previously 0, it toggles to logic level 1. In case of 1, 1, 1 is toggle state. If previously 1, then QB toggles to 0. In the same way, we can fill for QB plus 1 with x is equals to 1. With x is equals to 1, JB is 0 and KB is QA bar. KB is QA bar. KB is QA bar. So 0 and 1. 0, 1 is a reset state. 0, 1 is a reset state. QA is 0. So QA is 0. Its complement is 1. 0, 1 is a reset state. If QA is 1, its complement is 0. 0, 0 is a hold state. So hold state means if previously 0, it will remain hold. Now if QA is 1, KB will become 0. 0, 0 is a hold state. Hold state if previously 1, then QB plus 1 will remain in the hold state with x is equals to 1. Hoping all of you able to understand up to this part. Now if you observe output is QA XOR QB. So 0 0 XOR gate, for different it will give 1 and for same it will give 0. So we have a state table of the given Moore model. How many of you able to understand up to this part, beta ji? Great, sir. We can either assign them as a state variables, variable A, variable B, C, D, or we can keep the states as it is. So next is your state diagram. Now please observe state diagram, Moore state diagram. If we talk about Moore state diagram, we have 0 0 0 1 1 0 and 1 1. 0 0 0 1 1 0 and 1 1. Yes, sir. So we have a possibility of 0 0. This is QA QB. For 0 0, you can assign this as a state A. If you assign it as a state A, you can write state A. So if we have 0 0, then with x is equals to 0, next state is 0 1. So 0 0, what is the output for 0 0? Output for the 0 0 is 0. Output for the 0 0 is 0. Output for the 0 1 is 1. Output for the 0 1 is 1. Output for the 0 1 is 1. Output for the 1 0 is 1. Output for the 1 1 is 0. Now you can also write them as state A by 0, B by 1, C by 1, D by 1. Is it okay? Now if you are on present state 0 0 with x is equals to 0, present state 0 0 with x is equals to 0, next state 0 1. 0 1 is state B. So with x is equals to 0, we are getting 0 1 and output will become logic level 1. This is indicating present state. Present state. This is indicating output. This is indicating input. Arrow indicates going to next state. Now please observe, with the 0 1 as a present state, input x is equal 0 0 as a present state, 0 0 as a present state, with x is equals to 1, next state 0 0. X is equals to 1, x is equals to 1, next state 0 0. Present state 0 1, present state 0 1, with x is equals to 0, next state 1 1. Next state will become 1 1. Present state 0 1, present state 0 1, x is equals to 1, next state 1 0, next state 1 0, next state 1 0 with x is equals to 1. Present state 1 0, x is equals to 0, next state 1 1, x is equals to 0, next state 1 1. Present state 1 0 with x is equals to 1, next state 1 0. So with x is equals to 1, x 1 0. Present state 1 1, x is equals to 0, next state 0 0. So next state will become 0 0. Or x is equals to 1, next state will remain in D only. How many of you able to understand the Moore state diagram as well? Great. So now we have a Mealy state diagram as well as Moore state diagram. Hoping all of you able to understand the state diagram and their meaning, as well as you know how to identify the state diagram of any given finite state machine, whether it will be a Moore or a Mealy. Hoping all of you able to understand up to this part. Please let me know by writing in the comment section, beta ji. So Mealy and Moore model, now I am hoping all of you able to understand. Great. Next topic is your state reduction. Whenever user come to us, he will set certain set of conditions what he want to design. Okay, first we will try to understand their desire, and then accordingly we first draw the state diagram. After drawing a state diagram, we see is if there, it may be possible that user wants, user is saying like conditions, but the conditions are repetitive. So that we analyze, and first we draw reduced state diagram. Once we have reduced state diagram, then we can go with a reduced state table, and then write excitation table from the state table, then find the excitation equation, minimize it, and then we will implement the logic circuit and given back to the user that yes, your circuit get designed. Is it okay? Great. So this is a very important part of your entire digital electronics. If you really have a feeling of digital electronics now, I think this particular topic will gain your attention and give you a feeling of entire digital world, how the digital circuits are designed and how any logics are going to be built. Great. Hoping all of you able to understand up to this part. So next is your state reduction technique. So from state reduction technique, and then we will see sequence detector, overlapping, non-overlapping, tomorrow's class. Okay. Day after tomorrow we will discuss about the A to D, D to A converters, and then your digital electronics, this fast course of digital electronics will end up. So by this week, your digital electronics is going to complete, and then maybe signal or some other subject for the CS branch is going to be started. For electrical electronics, signal get started by 13th. Okay. So hoping all of you have enjoyed the part completed so far. Please let me know by writing in the comment section, beta ji. Have you enjoyed? Okay, so for the PDF portion, you can connect on Telegram. Again, I am posting this Telegram detail, and your PDFs will get uploaded after 2 days. Okay, but this I will upload by today only. So you can join this Telegram channel for any question required with your digital. You can scan and connect and ask. You will also able to download your PDF as well. Hoping you have enjoyed this session a lot. Lots of love, beta ji. Thank you everyone. We will meet again at 9 PM tomorrow. Thank you everyone. Good night.